Hi there, this is Dr. John, your physics and math professor. Even though this is a teaching channel, every once in a while I'm going to include something new, something to stimulate your imagination. In this video, I'll propose a new theory that ties together black holes with the expansion of the universe. This is an idea I've been contemplating for about 10 years, but only recently decided to turn it into a video. What is a theory? A theory, especially in physics, is a concept or an idea that will tie together two things that previously were not thought to be tied together. For example, Isaac Newton tied together the mass of an object with the force needed to accelerate it. James Maxwell tied together electricity and magnetism with these amazing formulas. And Albert Einstein tied together the apparent mass of an object with its speed. Before these concepts were presented, most people didn't see how these various things were tied together. But today, more and more scientists talk about the universe as being beautiful. It is massively organized, and all parts of the universe are somehow connected to all other parts of the universe. They believe that the more we understand, the fewer things will be off by themselves. For example, today we have the electrical, the magnetic, and the weak forces that seem to all be tied together. But gravity remains elusive. But most scientists expect that sooner or later, even gravity will be tied in with the others. The more we research the universe, the more we find this to be true. Everything is indeed tied together. Some of the latest research involves how electrons that were once close together but then moved far away remain tied together. It's called quantum entanglement. When one electron flips its spin, the other one also flips its spin, even though they are far apart. And the speed of this communication is faster than light. Now some think that the entire universe may somehow be entangled. So let me briefly explain the two concepts I'm going to try to entangle or tie together today. Stars have a tremendous amount of mass, but they don't fall in on themselves because the heat they produce pushes that mass outward. However, when they run out of fuel, they can fall in on themselves. The molecules get crushed, atoms lose their shape, and if gravity is strong enough, the electrons can even be pushed right into the protons. Remember, the inside of an atom is mostly empty space, just like the inside of our solar system is mostly empty space. If you were to take an atom and expand it to the size of the Earth, the nucleus might only be 200 meters across. If you were to take a spaceship inside an atom, you might not even be able to find the nucleus. But under the intense gravity, the electrons can get squished into protons to make a sea of neutrons. This is called a neutron star. One sugar cube of a neutron star would weigh 1 billion tons. Like the key to Superman's fortress of solitude that only he can lift, we know of nothing more dense. These neutrons are kept apart by the Pauli exclusion principle that says that two neutrons can't occupy the same space. But if gravity continues to crush, even this breaks down. And after that, there's nothing to stop the collapse, and the mass continues to fall into what is called a singularity, which means a nothingness. This forms a black hole. But in a crazy way, the mass inside a black hole has vanished from this universe into that pinhole of space. Meanwhile, outside the black hole, something else happens. Space-time itself, which defines what a straight line is, bends around masses. And around a black hole, it bends in such an extreme way that you could say that space-time itself breaks, it ruptures, hence the singularity. But this creates a mystery. Where did this matter go when it vanishes? This is one of the greatest mysteries in the universe. You can't have matter just vanish into nothing. We'll come back to that later. The second thing I want to entangle today is the expansion of the universe. But before I do that, I want to get back to and expand upon something I briefly mentioned before, and that is space-time. What is space-time? Well, nobody really knows. When I was studying graduate level physics at the university, my professors would talk about how a pendulum, let's say it was swinging at the North Pole and it was swinging in one direction and the Earth would be rotating under it. The Earth would rotate, but the pendulum would stay swinging in the same direction. And this just freaked me out. I didn't understand how could this possibly happen. How did the pendulum know that this was a straight line and the rotation of the Earth was not a straight line? My professor could not answer the question. I asked, is it communicating with the stars somehow and telling it what a straight line is? Nobody knew. This needs to be answered. This is one of the fundamental rules of Newton's laws. Something goes in a straight line unless acted upon. So somehow this pendulum has to know what a straight line is. Since then, we've come up with some other ideas. Maybe there's an invisible grid of virtual particles. We call this dark energy, and this forms the space-time continuum. This grid also contains energy. We call this the zero-point energy. That means that even if space was completely empty, had no atoms and no light in it, space would still be full of a dizzying array of particles that were coming in and out of existence, and it was these very particles that would define the space-time grid and allow a pendulum to go in a straight line. It also allows light to propagate. In the olden days, people thought that light moved through a medium of some kind, just like water or sound waves do. Then we threw that out. We thought that light propagated through nothing. Now we're coming back to some kind of media, maybe the space-time grid or dark energy. We might even say that light can't propagate without this grid. These space-time lines are everywhere that matter or light is, but these lines can also bend around sources of gravity. When Isaac Newton said that an object will continue to move in a straight line unless acted upon by an external force, he was mostly right. We today take that same principle, but we redefine what straight lines are by saying these are the straight lines created by the dark energy, and this dark energy bends under the force of gravity. So as far as space goes, curved is the new straight. Hence, this dark energy may be essential for the function and operation of our universe. For one, light can't propagate without it. If it could, then it wouldn't bend when space-time bends. Secondly, matter needs dark energy to recognize a straight line or to recognize spin, and all particles have spin, even light does. And this dark energy is such a massive part of the universe that it might define 75% of the mass or energy of the known universe. Here's what many scientists today believe about the mass of the universe. The matter that we see, the stars and planets, account for about 5% of reality. Dark matter, whatever that is, accounts for about 20%, and dark energy is the rest. So these two, visible and invisible matter, are forms of matter. And this is the grid that holds it all together. Why dark matter? Well, when people observed the rotation of galaxies, they realized that when they counted the mass of the stars and the planets, this was far short of the mass needed to allow the galaxies to keep their form and shape. Hence, there must be some form of matter that is basically invisible, but also provides gravitational attraction. And this dark matter also follows the line set by dark energy. With all this behind us, we come to the key question. The observed universe is about 100 billion light years in diameter. But what is beyond that? There is no lighter matter. There can't be, or the universe would be bigger. But could dark energy extend beyond that, say forever and ever? Well, if that was the case, then the universe would have to have an infinite amount of energy in it. We're always trying to get rid of infinities. More likely, as the universe expands, space-time expands with it. Now think with me for a second. As matter expands like in an explosion, it diffuses and becomes less dense. As light expands like coming from a flashlight, it diffuses as well and becomes less dense. However, the dark energy can't just expand and diffuse. This would dilute the nature of the underlying grid. It would probably affect the speed of light and other fundamental constants. But that means there must be new dark energy being created at the edge of the universe as it expands. But we don't like this. We like to believe in the conservation of energy. But in this case, it would be this. It would be the energy of visible matter plus the energy of invisible matter, that's dark matter, plus the energy of the dark energy. All that would equal a constant and needs to be conserved. This means that we must find ways to generate new energy, which allows us to build the space-time grid, which is then needed for the expansion of the universe. But where could this new energy come from? Or let's ask this question this way. Is there some other place in the universe where matter and energy are disappearing from the known universe? Yes, you guessed it, black holes. What if the matter and energy that is lost into black holes reappears as dark energy at the end of the universe, thus allowing or even forcing the universe to expand? That's my theory. Why should this idea even be considered? First of all, because of the already mentioned conservation of energy. We can't just create this massive amounts of new energy. It needs to come from somewhere. Secondly, black holes are a place where space-time is being ruptured, and the edge of the universe is a place where space-time is being created. Does it not seem reasonable that these two are related or even entangled? And thirdly, there is the math. Physics theories always require some sort of mathematics. So let's ask this big question. Can we calculate the amount of mass or energy lost into black holes and the amount of energy needed to create new dark energy at the edge of the universe? I made just such a calculation. The calculation is very rough with a lot of estimates, but let me share the results with you. For simplicity, I've done all my calculations in light years and in kilograms for energy. If you want to convert to actual energy, just multiply by the speed of light squared. And also all the numbers that I use can be found with a simple online search. You can check my numbers at home. At present, the size of the universe is considered to be 93 billion light years. So let's model the universe as a sphere with a radius of 50 billion light years. Now, how fast is the universe expanding? I spent a lot of time on this, went through a lot of iterations, but I think the simplest solution is to say the universe is expanding at the speed of light. For no matter what matter or energy there is, light has to be moving outward from the universe at the speed of light. So we'll just take it expanding at the speed of light. The surface area of a sphere is 4 pi r squared. And if we're expanding that at 1 light year, we can find the new volume being created by multiplying the area 4 pi r squared by 1 light year. That's going to give us the new volume being created. And we're going to have that in this formula right here. We get 4 pi r squared. Take the r is equal to 5 times 10 to the 10 light years. This calculates to be 3 times 10 to the 22 cubic light years. The total mass of the universe is this. And if this is the regular matter plus the dark matter, then the dark energy would be about 3 times this. Remember our previous chart. But how much new dark energy do we need to fill that gap that we're creating with the expansion of the universe? Well, the volume of the sphere is 4/3 pi r cubed, so the volume of the entire universe is this big number there. Now we take a ratio of the new volume created, that is the thin coating outside of the universe, this 1 light year coating. Take that volume divided by the total volume of the universe, and that should be equal to the new dark energy creating divided by the total dark energy in the entire universe. I have outlined that for you right here. Just cross multiply, match your powers, and you get x equals 2.7 times 10 to the 43 kilograms. This is the amount of mass, or convert to energy if you wish, needed to create the expanding dark energy every year. We'll put this number to the back of our minds and come back to it later. Now let's look at the mass destroyed inside a black hole. What do I mean by destroyed? Well, from what we know about black holes, the mass and the energy continue to shrink to this singularity that seems to vanish from our universe. Seems to, I say. Estimating the number of black holes in the universe and how much mass goes into them every year is a much harder and more difficult problem. Some estimate that there may be as many as 40 quintillion black holes in the known universe. Of these, they come in 2 main varieties, although there's others as well. First of all, there's the stellar-sized black holes. These are black holes about the size of our sun. Some believe there may be 100 million of these in our galaxy alone. And then there's the supermassive black holes found at the center of the galaxies. And people believe that there is a black hole like this at the center of every galaxy. I'm going to do my calculation using only the second of these, the supermassive black holes. And doing this calculation again is very simple. Just follow the math here. We're going to, again, all these numbers can be found with a simple online search. Let's assume that there is a black hole, a giant black hole at the center of each galaxy. Secondly, that there is 100 billion to 2 trillion galaxies in the universe. I'm going to use the upper estimation here. And the average supermassive black hole consumes about 2 solar masses every year. Our sun has a mass equal to 2 times 10 to the 30 kilograms. To count how much mass these supermassive black holes consume every year, just multiply these 3 numbers. This mass consumed, total gobbled up by black holes each year, is equal to the number of galaxies, your upper estimate, times the mass of our sun, times the number of solar masses consumed each year, and I get 8 times 10 to the 42 kilograms. Again, you can convert this to energy if you want to multiply by c squared. Now we come to the big reveal. Do you happen to remember how much energy is needed, in kilograms of course, each year to build the dark energy structure as the universe expands? Here it is. Drum roll. The mass needed for dark energy is 2.7 times 10 to the 43 kilograms. You might think that these numbers are a long way off from each other, and I agree, but consider this. This is the very first calculation I did, and aside from using the upper estimate and the number of galaxies in the universe, I made no attempt whatsoever to modify these numbers to make them look better for this theory. And this is the kind of calculation you can do at home. For that matter, any physicist in a restaurant could do these calculations on a dinner napkin. You can look up all these numbers yourself. I'm not trying to pull anything over on you. But when I did this final calculation, I was absolutely stunned by how close these numbers actually were. Unconnected phenomena should not be this close, especially when dealing with such cosmologically huge numbers. It makes it look like they are related. And secondly, notice that in my estimation, the energy consumed by black holes is about 1/3 of what is needed to fuel the expansion of the universe. But in my estimate, I only used the supergiant black holes at the center of galaxies. Some estimate there are 100 million other black holes just in our galaxy. I left those completely alone. I did this for 2 reasons. One, I was assuming that the supermassive black holes would consume a lot more mass than the smaller black holes scattered throughout the galaxy. And 2, Figuring out just how much mass these smaller black holes consumes is much more complex. If people want to further test this idea, this concept, this theory, the next step would be to refine the estimates on the amount of mass being consumed by all the black holes in the universe. This is very difficult and will require help from astrophysicists and some complex mathematical analysis. Or maybe some of you out there can do it. When somebody does this calculation, I would not be surprised if these two numbers converge. And if that is the case, this opens up an entirely new understanding of the universe. If this theory is shown to be reasonable, that implies that the inside of black holes are somehow connected to the edge of the universe. Maybe this is some kind of dark energy entanglement. Or there's an underlying component of our universe, the dark energy realm, like another dimension, if you please, where travel faster than the speed of light is possible. And it could well be that it is these very black holes that cause or fuel the universe to expand. Thanks for watching. Don't forget to like and subscribe. If enough of you like and subscribe and share this video, I'll be able to make more like it. And don't forget, by subscribing, you'll also be able to help me to train high school math and physics students. So I will see you later. Bye-bye.